All right, let's continue. How do we show uniqueness? Generally, one of the most common ways how we show that something is unique, we assume that there are two different ways to do something, and then we show that they must coincide. So let's assume that n equals qd plus r, but at the same time that it equals q1d plus r1. But in the way where both r and r1 are less than d and greater than or equals 0. Okay, then what? Then let's assume that, so when we compare q and q1, one of them is greater than or equal than the other. It doesn't matter which one. Let's say we say that without loss of generality, assume that q is greater than or equal q1. Then we get d's on one side and r's on the other. Then we get the following: q minus q1 times d. I subtract q1d and factor out d equals r1 minus r. Then what happens? This number is not negative because we assume that q is greater or equal to 0. So this number q minus q1, there are two cases. Q minus q1 is 0, or q minus q1. Shall I go to contradiction? Why not? Q minus q1 is greater than or equal to 1. Because if you have positive integer, then it's either 0 or it's 1 or above. If q minus q1 is 0, then that means that q equals q1. But also since this is 0 and r equals r1, so that's exactly what we want, that they are equal, that it's unique. What if q minus q1 is greater than or equals 0? That will give us contradiction. Why? Because look at this, q minus q1 times d. If this is greater or equal 1, the left side, left side is greater than or equal d, because this is at least 1 times d is greater than or equal d. The right side is less than or equal r1 because you are subtracting a positive number, but r1 is less than d. So look at this, left side is greater than d, the right side is less than d, contradiction. So this contradiction shows that this cannot happen, this must happen, and we have our uniqueness. These proofs are already a little more subtle than what we had before. It's not like just crossing the river, writing equations. So you have to organize it a little bit, and I assume that you feel that these proofs are slightly more complicated, but that we shouldn't panic about it. Just the main thing is to remember what the statement of the theorem and the meaning of it. So example, we already did an example. How do you find quotient and the remainder when we divide positive numbers? Let me do one more example for negatives. So for negatives, and while writing a proof, I already mentioned that for negative story works a little differently. So here it is. Let me use the same factorization for 31 to get factorization, not factorization, sorry, quotient remainder theorem for negative 31. So find or apply quotient remainder theorem on negative 31. So I'll say the following. Let's say, and that's really what you can do. You can write a program so that you never work with negatives, only work with positives. So we already did for positives. So do it for 31 first. So 31 equals 4 times 7 plus 3, as we already did it. But then multiply by negative 1. So we get negative 31 is negative 4 times 7 plus negative 3. But we cannot report that because our remainder is negative, and you are not allowed to have a remainder to be negative. So here's what we'll do. Add an extra negative 7 here, and add a positive 7, which doesn't change anything. Negative 7 and 7 is 0, so generally what are we going to get? Now we have not negative 4, but negative 5 sevens. And the 4. Here it is. This is now really quotient remainder, because my divisor is 7, my quotient is negative 5, my remainder is 4, and you remember remainder has to be between 0 and the d, and that's the way to do it. So you actually have to spend an extra 7 and then decrease the quotient to become more negative in order to make remainder. Remainder has to be positive, no matter if your number is positive or negative. All right. So this is the main content of our section. I just mentioned some notation that's used in our course and even more in computer science, so that you are aware of it when it appears in different examples or different courses. But actually the main content of the section is already achieved. So first, the notation of floor and the ceiling. So definitions are in the notes. So what is the floor of a real number? So if x is a real number, then floor of x is an integer m such that x is greater than or equal m, but less than m plus 1. So what is that? So let me see floor now. The floor. So what does it mean? That's basically if x is 7.39, then floor of x, you round it down, is 7. The same way you also, and if x is negative 7.39, then floor of x is negative 8. You have to go down always to get integer. Of course, if x is integer on its own, then floor of x is just 7. And finally, there's also the other function where you round it up, and that's called the ceiling of x. So here's the ceiling, and the symbol and the name tell you basically what it is equal to m if x is less than or equal m and greater than m minus 1. So for example, if x is again our 739, then ceiling of x will be 8. And that's the notation about floor in there and the ceiling. And let's prove one statement about floors and ceilings. Those are actually examples of proofs where we, let me try to keep definition, and hopefully I'm not getting out of the camera's window. So we want to prove example 2.4.8, and we wanted to prove the following: if x minus floor of x is greater than or equal to 1/2, then floor of 2x equals 2 floors of x plus 1. Generally, when you look at this statement, it really looks awkward because we never worked with algebra involving floors and the ceilings, and that's very dangerous because you cannot assume that rules that normally work in algebra work. So we use algebra only on the expressions that we are familiar with, plus, times, and all those. So on the ceiling and on the floor, I really have no idea what to do. So what do we do then? Again, we are escaping to a known territory. So I'll say the following.
let me tell you basically what does this statement say. So this is not proof, but just illustration. If number is somewhere here, so that's it in the integer part, and it says so here's your integer part. Here's your round down. Here's your round up. But here it says you are quite further away from your round down. So then you are somewhere here, not here, you're not close to your floor, you are fairly far. And then what happens? When you double your number, the fact that you have here more than half after doubling will give you an extra 1. So generally, instead of just doubling the floor, you actually double the floor and get an extra 1. So it should make sense. Let's see, how do we write that? So we say the following. So I want to go to definition, and I'll give the name to the floor of x, and I'll call it k. So we have a name for the object, helps me to work with it, and it says, you are the floor. That means I'm at least as good as you are. X is greater than or equal k, and less than k plus 1. But actually, they gave me even more here. They said x minus k, because floor of x is k, is greater than or equal than a half. So actually it tells me that x is greater than or equal not only than k, that k plus 1/2. So I know more. So here, actually this gives me that x is between k plus 1/2 and k plus 1. What now? Now this is inequality with standard algebraic operations that I know from before. So now another problem, just multiply by 2 both sides, and we get the following: 2 times k plus 1 less or equal to x less than 2k plus 2. You see, a minute ago I told you exactly the same thing, but it was more verbal, visual. Here I have formal proof. So 2x less than 2k plus 2 greater than or equal to k plus 1. So what is this telling me? I squeezed my number between two consecutive integers so that it's greater than or equal the left one and less than the right one. That's exactly the definition of a ceiling. I'm sorry, of a floor. So generally from here, by definition, that means that the floor of 2x is the left one, which is 2k plus 1. Now I just recall that actually k stands for floor of x plus 1 done. This is the end of. Very often people here put a box. I never told you about that. Or people say QED. You probably saw it in some book. That's from Latin, quod erat demonstrandum. What was needed was proved. So it's good also to be aware of these two functions. As I said, they are used often in computer science. So I would like you to be familiar with them and to see if you want to do proofs about floor and the ceiling, you have to always go to this definition, and then you deal with the known object, which are our known equalities and inequalities, and then things are much better.